In this video, we're going to continue our discussion on polynomials and talk specifically about the zeros of polynomials. There's a lot of different theorems in this video and a lot of different techniques to use to try to find all the zeros. It's going to be pretty involved. We're going to start with the rational zero theorem. So the rational zero theorem tells us about what the possible rational number zeros for a polynomial could be. Now remember, a rational number is one that can be expressed as a fraction. It's a ratio of integers. So it's not something like pi, that's an irrational number. It can't be written as a fraction. But anything that can be written as a fraction, not complex numbers, just integer over integer. So if f of x is a polynomial that looks like an x to the n plus an minus 1 x to the n minus 1 all the way through a1x plus a0. If this function has integer coefficients and an is not 0, and if p over q is a rational zero of f, then p is a factor of a zero and q is a factor of an. So that sounds pretty complicated, but what this is saying is if you have a rational zero, it's going to be of the form factor of your constant term divided by factor of your leading coefficient. So let me write that real quick. So this just says if there is a rational zero, it is of the form plus or minus a factor of your constant term over a factor of your leading coefficient. Now, notice that's a big if there. We can list all the possible rational zeros, but it's still possible that those aren't zeros of your polynomial at all. You would still have to verify it actually is a zero. But this theorem here gives you a starting point to try to find zeros, rather than just guessing random numbers until you find one. It at least lowers the number that you have to check. So let's go ahead and do an example where we list every single possible rational zero of a polynomial. So list all possible rational zeros of f of x equals negative 4x to the fourth plus 5x to the third minus 7x squared plus 8. So the way we're going to do this is I would suggest you first list all of the factors of your constant and all of the factors of your leading coefficient. So your factors of your a0, which is your constant 8, well, just think about what numbers can be divided into 8 evenly. 1, 2, 4, and 8. And of course, positive or negative for all of those. And now factors of our leading coefficient. Well, my leading coefficient is negative 4. So I'm going to have what things divide negative 4 evenly? Plus or minus 1, plus or minus 2, or plus or minus 4. So now if I want to list all of the possible rational zeros, these possible factors of 8 go on the top, and the possible factors of -4 go on the bottom. So I'm going to start by writing all of the possibilities that have a 1 from my factors of 8. So I can have 1 over 1, 1 over 2, or 1 over 4. So that's using this plus or minus 1 over all of the choices for the denominator. Now I do the same thing with the 2. Plus or minus 2 over 1, plus or minus 2 over 2, plus or minus 2 over 4. Do it again with the 4. 4 over 1, 4 over 2, 4 over 4, and then we just have that 8 left. 8 over 1, 8 over 2, or 8 over 4. So that will be every single possibility, but we have some repeats in here. So if you're actually trying to just write the possible rational zeros, you want to make sure you're not repeating choices. So I'm going to be simplifying all of the fractions, and if I get a repeat, I'm not going to write it down a second time. So my possible rational zeros well, 1 over 1 is just 1. So I have plus or minus 1, then I have plus or minus 1/2 and plus or minus 1/4. Then I have plus or minus 2. 2 over 2 is 1. I already have that right here. 2 over 4 is 1/2. We already have that choice. 4 over 1, that's 4. So plus or minus 4. 4 over 2 is 2. I already have that written down. 4 over 4 is 1. We already have that. 8 over 1, we get plus or minus 8. 8 over 2 is 4, we already have that, and 8 over 4 is 2, we already have that. So here are all of my possible rational zeros. So if you were told to find all the zeros of that polynomial, these are some of the numbers you could try first, because if there's going to be a rational zero, it's going to be in this list. Let's do an example where we actually find all of the zeros using this rational zero theorem to help us. So example, find all of the zeros of the function f of x equals x to the third minus 4x squared plus 3x plus 2. And we're going to start by guessing some zeros by listing all the possible rational zeros first. So my possible rational zeros remember, it's going to be the factors of the a0 over factors of my an. So factors of a0 are just 1 and 2. So I have plus or minus 1 over 1 and plus or minus 2 over 1. The only factors I have in my leading coefficient are plus or minus 1. So this one's a lot less possibilities than our last example. When I simplify this, this means my possible rational zeros are plus or minus 1 or plus or minus 2. So we have 4 possibilities there. So let's start by trying to see if any of these actually are a zero. We're going to use our synthetic division to help us with that. Let's start with x equals 1. Is that going to be a 0? Well, to find that out, we can do synthetic division with a 1 in the box, put our coefficients of our polynomial over here, and do synthetic division. If 1 is a 0, we'll end up with a remainder of 0 at the very end. So if you don't remember synthetic division, it's actually talked about in the video just before this. If If you need a refresher on that algorithm, I would stop this video right now, go rewatch that part in the previous video, and then come back to this. All right, so doing our synthetic division, 1 times 1 is 1, add together. -3 times 1 is -3, add them together. 0 times 1 is 0, add them together, and I got a remainder of 2. This means that this is not going to be a 0 of this particular function. So x equals 1 is not a 0. Let's try the next one in our list, -1. So if I try x equals -1, I would put -1 in the box, all of my coefficients, and do my synthetic division. Drop your 1, multiply and add, multiply, add, multiply, and add. And I did not get 0 as a remainder again, so this also tells me no. X equals -1 is not a 0 of this polynomial either. So we've already eliminated positive and -1. I guess let's try +2 and see what happens. So if I try x equals 2 to see if it's a 0, 2 in the box, all of my coefficients, drop your 1, multiply and add, multiply and add, multiply and add. So this time I got a 0 as the remainder. And that 0 as a remainder tells me that yes, I have a 0 of my polynomial. So x equals 2 is one of my zeros, but I'm not finished yet. That just tells me one of my zeros. So at this point, I know x equals 2 is a 0, and that tells me that x minus 2 is a factor. That's from our factor theorem last time. I can then write my original polynomial as x minus 2 times the result of this synthetic division. So right now, I know my polynomial f of x is equal to x minus 2 times this guy, which is x squared minus 2x minus 1. That is my polynomial rewritten. So this is mostly factored. I know all of my zeros to this polynomial are going to be solutions to this equation. And this guy, the x minus 2, we already know that's 0. X equals 2 was the solution we already found. The rest of my zeros come from 0 equals x squared minus 2x minus 1. And we know how to solve that because that is a quadratic equation. You could try to factor it. It's not going to work too well for this particular problem. You could try completing the square, though I personally don't like to do that too much. I'd probably use the quadratic formula on this one. The quadratic formula tells me x is equal to my negative b, so that's positive 2, plus or minus the square root of b squared minus 4ac all over 2 times a. And if I simplify this, I will get all of the other zeros for my original polynomial. So I get x equals 2 plus or minus a square root of 4 plus 4 all over 2. So that is 2 plus or minus square root of 8 over 2. And I just have to simplify this to get the rest of my zeros. Remember to simplify your square root of 8, find things that multiply to 8 and break it all the way down. If you have a pair, that comes out of the root, and anything left unpaired stays underneath the root. So I get x equals 2 plus or minus 2 root 2, all divided by 2, which when I simplify, that is 1 plus or minus square root of 2. And now I have all of my zeros for the original polynomial. We have x equals 2, which we figured out using our rational zero theorem, and then checking using synthetic division and our factor theorem. And then over here, factor and remainder theorem, I think we used both. And over here, we got our other zeros by taking the result of our synthetic division, setting it equal to 0, and solving a quadratic equation. That was a lot of work for one problem, and that's how most of this video is going to be. So it's I think it's a lot of fun trying to find all of the zeros. You probably don't think it's quite as fun, but hopefully you at least understand how we got to where we got. Now, one of the trickiest things about these problems is knowing where to start. Sometimes you're going to want to start with that rational zero theorem. Other times you might be able to just factor right away. You just have to look at the particular problem to figure it out. Let's do another one. Find all the zeros of the polynomial f of x equals x to the fourth minus x squared minus 20. Now, this particular one, I would jump directly to factoring. Now, you might be wondering how you're going to factor that. This does not look exactly like a quadratic equation. And you're right, it's not quite there, but it's very, very similar. If this looked like an x squared minus x minus 20, we'd be good to go. So I'm going to do something called substitution. I'm going to make up a new variable just to make my life easier. I'm going to call it u. And I'm going to say u is equal to x squared. That means that I can then rewrite my x to the fourth minus x squared minus 20 as u squared minus u minus 20. Take a look at that for a second. This x to the fourth is the same thing as x squared squared. That's why I wrote it as u squared. This x squared, I call that u. Now I can solve this quadratic equation for what u is equal to, and then plug u equals x squared back in and figure out x. So I have u squared minus u minus 20 equals 0. That I can factor. What multiplies to negative 20 and adds up to negative 1? Well, that's going to be a negative 5 and a positive 4. So I have u minus 5 times u plus 4. Then I use my zero product property to set each factor equal to 0. And I solve those to get u equals 5 or u equals negative 4. But we're not done, because my original problem had x's and not u's. So now I get to take this u equals x squared and plug that back in. So since u is equal to x squared, I know x squared is 5, or x squared is negative 4. Take a square root. X is plus or minus the square root of 5. And on this side, I get x equals plus or minus the square root of negative 4. That one I can simplify further. I would have a plus or minus the square root of 4 is 2. And the square root of the negative gets me an I. So x is plus or minus 2i. This guy doesn't simplify further. X is plus or minus square root 5. So I have 4 different zeros for this particular polynomial. Now, we could have done it different. You could have used the rational zero theorem, but take a look at what we got for our zeros. If you tried to use the rational zero theorem on this one, none of the possible rational zeros would have actually worked, because I didn't get any rational numbers for my zeros, so we would have still been stuck and would have had to figure out a way to factor this. Now, you might have noticed on this problem, we ended up with 4 zeros, and the degree of my polynomial was 4. Is that a coincidence? No, it's not. It's actually called the fundamental theorem of algebra. So, the fundamental theorem of algebra states that if f of x is a polynomial of degree n, which is bigger than or equal to 1, and this polynomial has complex coefficients, then f has at least one complex zero. And in fact, your f of x has exactly n zeros when we count with multiplicity. So this means if you have a polynomial of degree n, there's going to be n zeros. Some of them will be real numbers, some might be complex numbers, but you'll have n of them in total. Whatever the degree is, that's the number of zeros you're going to find. Counting with multiplicity, that just means, remember when we had a 0 with multiplicity 2? Let's say we had a 0 of x equals 1 and it had multiplicity 2. That means out of my n zeros, I'm going to have x equals 1 listed 2 times, so it counts twice. All right. Now, I have another theorem that helps us an awful lot with finding our zeros. It's the conjugate zeros theorem. So the conjugate zeros theorem states that if f of x is a polynomial with real coefficients, and if a plus bi with b not equal to 0 is a 0 of f of x, then its conjugate, a minus bi, is also a 0 of f of x. This just says that your purely complex zeros, the ones that have i's in them, they come in pairs. You have conjugate pairs of zeros. So if you know 2 plus 3i is a 0, then you know 2 minus 3i is also a 0. And this helps quite a bit in finding our zeros. Let's do an example. Given f of x equals x to the 4th minus 2x to the 3rd plus 28x squared minus 4x plus 52. And that 1 plus 5i is a 0 of f of x. We are going to find all of the zeros. And then we're going to factor f of x as a product of linear factors. All right, well, before we even start this problem, let's just first figure out how many zeros we're looking for. We need to find all of the zeros. The degree of my polynomial is 4. My fundamental theorem of algebra tells me that that means I have 4 zeros total. 1 plus 5i is one of those zeros. By my conjugate zeros theorem, I know 1 minus 5i is also a 0. So I already know 2 of the 4 zeros. We just have to find the other 2. How we're going to find the other 2? Well, let's just do some synthetic division using the zeros that we know, and maybe we'll be able to figure out the other ones. So, for part A, I know that 1 plus 5i is 0. So I'm going to use synthetic division with that 0 and the coefficients of my polynomial. So that is 1, negative 2, 28, negative 4, and 52. And I'm going to use synthetic division to see what's left after I would have this factor taken care of. You drop the 1. 1 times 1 plus 5i is 1 plus 5i. So that will get me negative 1 plus 5i. Now, if I multiply those guys out, well, what would we get? 1 plus 5i times 1 minus 5i. Sorry, I wrote that down wrong. 1 plus 5i times negative 1 plus 5i. Let's see what we get. 1 times negative 1 is negative 1. I have plus 5i. I have minus 5i. And 5i times 5i is 25i squared. But we know I squared is negative 1. So this is really minus 25. I put it all together and get negative 26. I feel like I multiplied something wrong. Nope, that was right, negative 26. I was expecting i's to stick around still. All right, so when I multiply those two guys together, I get negative 26. Now when I add those together, I have 2. 2 times 1 plus 5i is 2 plus 10i. When I add those columns together, I get negative 2 plus 10i. And now I have to do that multiplication. I know the final result should be 0 because I was told this is a 0, but we should still double check to make sure we did the rest correct. So 1 plus 5i times negative 2 plus 10i. I get 1 times negative 2, which is negative 2. I have a plus 10i. I have a minus 10i. And 5i times 10i is 50i squared. Well, I squared again is negative 1, so this is really negative 50. So combining like terms, I get negative 52. Which is good news because that means I have a 0 as my remainder, like I was supposed to get. All right, now just a reminder for us before I do my next set of synthetic division. This guy here would be a constant term. This is my x. This is my x squared, and this is an x to the third. So this is what I get when I divide using my 1 plus 5i as my 0. Now I know 1 minus 5i is also a 0. So I'm going to use that information. Since 1 minus 5i is also a 0, I can do synthetic division again, using 1 minus 5i in the box and using my result from my last synthetic division as my coefficients. So let's see what we get when we do that. So doing synthetic division again, 1 minus 5i is my 0. The coefficients that I just got from my last result were 1, negative 1 plus 5i, 2, and negative 2 plus 10i. And do your synthetic division. So 1 times 1 minus 5i is 1 minus 5i. Add those columns together and you get 0. 0 times 1 minus 5i is 0. 2 plus 0 is 2. And 2 times 1 minus 5i is 2 minus 10i. So I get a remainder of 0 again, which we knew we were supposed to because we knew this one was a 0 as well. So this tells me, here's my new constant term. This would be x, and this one would be x squared. So the polynomial so far has zeros 1 plus 5i and 1 minus 5i. And the other zeros come from our result here, x squared plus 2 equals 0. So I just have to solve this last thing, the result from doing synthetic division twice, and set that equal to 0, and that will get you all of the other zeros. So let's solve that, and then make sure we have 4 zeros in total. So x squared plus 2 equals 0. I would use my square root property to do this. X squared equals negative 2, which means x is plus or minus the square root of negative 2. That's the same thing as plus or minus I times root 2. Those are my other two zeros. So we knew we had a 4th degree polynomial, so we knew we needed 4 zeros. My zeros are 1 plus 5i, 1 minus 5i, positive I square root of 2, and negative I square root of 2. So we do have 4 zeros just like we needed. All right, so that was part A. Part B was to write our polynomial as a product of linear factors. Well, the good news is now that we have all of the zeros, we know that if c is a 0, then x minus c is a factor. So I can write all of my factors by just doing x minus my 0. So x minus 1 plus 5i is a factor. Another factor is x minus 1 minus 5i. And then my other two factors are x minus I root 2 and x minus a negative I root 2. Which that last one, that minus a negative, I can write as positive. So a product of linear factors is x minus 1 plus 5i, x minus 1 minus 5i, x minus I root 2, and x plus I root 2. And now it's fully factored into linear factors. That last guy got a little bit smushed there. Let me rewrite it so it's a little easier to see it. That's a little bit better. So there we have it fully factored. So was that a lot of work? Yes, it was. But we were able to find all of the zeros of our polynomial that way. Let's do another example. Find a third degree polynomial f of x with integer coefficients and zeros 2 plus I and 4/3. Well, let's take a look at what we have here first. We want a third degree polynomial, and that means we need to have 3 zeros. But I was only told 2 of them. Do we know what the third zero is? Yes, because I know 2 plus I is a 0, so 2 minus I is also a 0 by my conjugate zeros theorem. So I know all of my zeros, all 3 of them are 2 plus I, 2 minus I, and 4/3. So I can start finding this polynomial by writing it in factored form. I know since all of those are zeros, then I have x minus 2 plus I, x minus 2 minus I, and x minus 4/3 are factors of this. So now I can just do a bunch of distribution to make sure all my coefficients are integers, and I would be finished. Now, I don't even know that this is going to work yet, so what we should do to be 100% safe that this is our polynomial is I'm going to put an a in the front, because we know we might need to multiply by a constant to get rid of having non-integer coefficients. It's possible that this a might end up being 1 and we won't need it, but just in case, we're going to put it there and we might end up needing it. So let's start with distributing. I guess let's distribute the 2 factors that have i's first. So I'm going to have f of x equals my a times, I have x times x, that's x squared, x times a minus 2 minus I. Wow, that was a mouthful. So that's x times a negative, so that makes it minus x with a 2 minus I. Now I'm going to do this minus 2 plus I times x, so that's a minus x with a 2 plus I. And then I have those 2 guys multiplied together. Negative times negative makes it positive, and I have a 2 plus I and a 2 minus I, which we'll figure out in a second. And then I still have x minus 4/3 that I'm going to deal with later. So inside that giant set of parentheses, let's do some more distribution and try to simplify this. Okay, sorry about that. So what we have here, f of x equals a times, I have an x squared. When I multiply this out, I get a minus 2x and a plus xi. Then I get another minus 2x and a minus xi. Now let's multiply all of this out. 2 times 2 is 4. I have a minus 2i. I have a positive 2i and a minus I squared. And then I still have x minus 4/3 on the very outside to deal with. All right. It's getting a little simpler. I have my a. Let's combine like terms inside of this set of parentheses. I have an x squared. I have minus 2x and another minus 2x. That's minus 4x. The xi's cancel out. My 2i's also cancel out. So I just have 4 and a minus I squared. I squared is negative 1. So this is a minus negative 1. That's plus 1. 4 plus 1 is 5. And we're almost there. That's starting to look a little bit better. Now we need to multiply this x squared minus 4x plus 5 times that x minus 4/3. Do all of that distribution and we'll see what we get. So we have f of x equals my a times x squared times x is x to the 3rd. Then I have a minus 4/3 x squared. Then this gets me a minus 4x squared. And a positive 16 over 3x. Then I get a 5x. And 5 times negative 4/3 is negative 20 over 3. So that's what my function looks like right now. And you can see we're not going to have integer coefficients. But what we can do to take care of that is think about what we would have to multiply by to get rid of all those fractions. All of the fractions have a 3 in the denominator. So if I use a equals 3, that will get rid of all of my fractions. So 3 times x to the 3rd minus 4/3 x squared minus 4x squared plus 16/3 x plus 5x minus 20 over 3. And now if I distribute that 3 through, I'll have my final answer of my polynomial with those particular zeros with integer coefficients. I get f of x equals 3x to the 3rd minus 4x squared minus 12x squared plus 16x plus 15x and minus 20. And now if I just combine like terms, we'll have it as simplified as we can, and that will be our solution to the problem. So we get f of x equals 3x to the 3rd minus 16x squared plus 31x minus 20. And that is a 3rd-degree polynomial with integer coefficients with the roots that we were told, which were 2 plus I and 4/3. It also has 2 minus I as its other zero, which we knew from our conjugate zeros theorem. All right, let's do another one kind of like that. Another example. Find a polynomial g of x of lowest degree with zeros, -3 with multiplicity 2, and 5 with multiplicity 2. And we also want it to satisfy g of 0 equals 450. So we want to find a polynomial with the smallest degree possible that has these particular zeros and a y-intercept of 450. How are we going to do that? Well, we're going to write it in factored form first. First, notice that I have a total of 4 zeros here. Multiplicity 2 for that one, multiplicity 2 for that one, so that's 4 zeros. This means that I need a degree 4 polynomial. So I'm going to write this in factored form. G of x equals, I might have some number in the front, we'll figure that out later. My 0 of -3 means I have a factor of x minus a -3. That's x plus 3. Multiplicity 2 means it's squared. A 0 of 5 means x minus 5 is a factor. Multiplicity 2 means it's squared. So now I'm going to multiply all this stuff out to figure out what g is. I'm going to take care of squaring these individually first. So we have g of x equals a times x plus 3 squared, remember, is x plus 3 times x plus 3, and you distribute. I'll get x squared plus 6x plus 9. Similarly, for the x minus 5 squared, we get x squared minus 10x plus 25. Now, if I distribute all of this, I have my a times x squared times x squared is x to the 4th. X squared times -10x, -10x cubed. X squared times 25 is 25x squared. 6x times x squared is 6x to the 3rd. 6x times -10x is -60x squared. 6x times 25 is a positive 150x. Now distributing my 9, I get a 9x squared, a minus 90x, and 25 times 9, which is 225. And that could be my polynomial. But let's go ahead and combine some like terms and see what it is a little bit simplified. So when I combine my like terms inside of those parentheses, we have our a times x to the 4th minus 4x to the 3rd minus 26x squared. Is that right? Yes. I didn't see that guy there. 26x squared, a plus 60x, and a plus 225. And now we just have to figure out, is this my polynomial? It has the correct zeros. It has the least degree possible for a polynomial with 4 zeros. The only thing we have left to check is g of 0 equal to 450? Well, what happens if I plug a 0 in for all of my x's? I'm supposed to get 450 for my g of x When I plug 0 in for all of these x's, everything disappears except for my a and 225. Now I can figure out what a is supposed to be. If I divide both sides by 225, I get that a is 2. So that means that my g of x is 2 times x to the 4th minus 4x cubed minus 26x squared plus 60x plus 225, which if I distribute that 2, we'll have the polynomial completely written out. Distribute the 2 and you get that our polynomial is 2x to the 4th minus 8x cubed minus 52x squared plus 120x plus 450. And that polynomial has the smallest degree possible to have the zeros we were given with the appropriate multiplicities, and it satisfies g of 0 equals 450. That was a lot of work, but that's okay. So to finish this video up, we just have 2 more things to learn and an example of each. So first we're going to learn about Descartes' rule of signs. Now this rule says, let f of x be a polynomial with real coefficients, and a non-zero constant term. Then 2 things are true. The number of positive real zeros is either equal to the number of sign changes of our polynomial, or less than that number by a positive, even integer. And we also have info about the number of negative real zeros. The number of negative real zeros is either equal to the number of sign changes of f of negative x, or less than that by a positive, even integer. So this sounds really confusing, but it's really not that bad. For this positive zeros, the sign changes we're talking about are how many times you change from a plus to a minus or a minus to a plus when you just read across your polynomial. Let's just say that that happens 4 times. Well, then the number of positive real zeros is either going to be 4 or 2 or 0. So you just subtract even integers from the number of sign changes, and that tells you the possibilities. Same for the negative real zeros, except you have to find f of negative x first. Let's do an example because it makes much more sense with an example. So determine the number of possible positive and negative real zeros of g of x equals 8x to the 6 minus 5x to the 7th plus 3x to the 5th minus x squared minus 3x plus 1. Well, the first thing we should do is rewrite this so that it looks like it's in the correct order. Notice that I don't have everything going in the proper order. I have this x to the 7th after the x to the 6th. So let's rearrange it so it's in the right order first. G of x is equal to negative 5x to the 7th plus 8x to the 6th plus 3x to the 5th minus x squared minus 3x plus 1. So to figure out the number of positive real zeros, we need to figure out the number of sign changes for this function. Well, here I changed from negative to positive, so that's a sign change. This goes positive to positive, that's not a sign change. But positive to negative is, negative to negative is not, but negative to positive is. I have 1, 2, 3 times we change signs. So that means the possible positive ones, we could have 3 positive real zeros, or we could have 1, because that's less than 3 by a positive integer, even integer. So you subtract 2 until you reach where you would get negative numbers going on. So it's either 3 or 1 positive real zeros. Now let's find negative real zeros. To find the negative real zeros, we're going to need to look at g of negative x. So I'm going to plug a negative x in for everything. And just remember that when you plug a negative x in, it's going to be negative if it's to an odd power, but it's going to be positive if it's to an even power. So I'm going to have a negative 5 times a negative x to the 7th. So that's going to be 5x to the 7th. The next one's to an even power, so it makes it positive. This one's an odd power, so it would be negative. This one's even power, so it'd be positive, but I have a minus in front. This one, negative 3 times a negative x would be positive 3x. And then my 1 has not changed. So that's g of negative x when it's simplified. Count the number of sign changes. I change from positive to negative, and from negative to positive. Just twice we change signs. So this means that the number of negative real zeros is either 2 or 0. Well, how many zeros does it have altogether? We know that this polynomial has to have 7 zeros altogether. So this means that all the other ones are going to be complex zeros. When we take a look at all of this information put together, here's positive real zeros, negative real zeros, or complex zeros. I know my total has to be 7. So we had, for the positive ones, there's either going to be 3 or 1. If I have 3 real positive zeros, and I could possibly have 2 negative real zeros, I know I have to have 7 zeros altogether, so this would make it so I had to have 2 complex zeros as well, so it adds up to 7. But it's also possible that I have 3 positive reals, 0 negative reals, but that means I'd have to have 4 complex zeros to still have a total of 7. Now, my other possibility for positive reals was 1. If I have 1 positive real, I could have 2 negative reals. That would be 3 so far. That means I'd have to have 4 complex zeros to make it 7 down there. And the other possibility would be 1 positive real, 0 negative reals, and that would have to have 6 complex zeros to make my 7 total. So those are all the possibilities of what the zeros are going to look like. One last theorem for this video helps us figure out a range of values that we can look for our zeros. So we have the upper and lower bound theorem for real zeros of a polynomial. So the upper and lower bound theorem for the real zeros of a polynomial. This theorem says if f of x is a polynomial of degree n greater than or equal to 1 with real coefficients, and a positive leading coefficient, and is divided by x minus c, then we have 2 things that are true. First thing, if c is positive and the remainder and quotient have all non-negative coefficients, then C is an upper bound for the real zeros. What this means is if you are dividing your polynomial by x minus c, and c is a positive number, if when you do all of your division, synthetic or long division, all of the coefficients are non-negative and your remainder is non-negative, then that c is an upper bound for your real zeros. An upper bound is just a number that is greater than or equal to all of your real zeros. So it chops off all the possibilities and says all of the real zeros are going to be less than this number. My second fact is if C is negative and the coefficients of the quotient and remainder alternate in sign, and we take 0 is positive or negative as needed, then C is a lower bound for the real zeros. So this just says if that C is a negative number, and when you do all of your division, you alternate between positive and negative, and 0 counts as either one, depending on what you need it to be at the time, then you're going to have a lower bound for your real zeros. That's a number that's less than or equal to all of your real zeros. So we're going to just finish up with one example using this theorem, and that will be it for this video. The last example. F of x equals x to the fourth minus 2x to the third minus 13x squared minus 4x minus 30. Part A. Does the theorem that we just talked about identify 4 as an upper bound? And let's answer this part A before we even write down what part B is. So to figure out if 4 is going to be an upper bound, we need to divide this polynomial by x minus 4. I'm going to use synthetic division to do that. So I would have a 4 in the box, and we put our coefficients next to it. 1, negative 2, negative 13, negative 4, and then negative 30. We know that this is going to be an upper bound if I get all positives down on the bottom. So 1 times 4 is 4, add to get 2. 2 times 4 is 8, add to get negative 5. I already know from that point that this is not going to be an upper bound, because I got this negative right here. I don't even have to finish up the rest of it. I already know that 4 is not guaranteed to be an upper bound for my real zeros. Part B. Does the theorem identify negative 4 as a lower bound for our real zeros? Well, for that, we're going to do synthetic division again. Negative 4 in the box, put all of our coefficients next to it, and do synthetic division. Now remember, for the lower bounds, we need it to be alternating in sign all across the bottom for it to be a lower bound. So I start with a positive. 1 times negative 4 is negative 4. I add and I get a negative. So far we are alternating. Negative 6 times negative 4 is positive 24. And then add that column, I get positive 11. And we're still alternating. 11 times negative 4 is negative 44. Add to get negative 48. And that's good, we're still alternating. Negative 48 times negative 4 is 192. 192 and that negative 30 is 162. So all along the bottom, you see we're alternating positive, negative, positive, negative, positive. So yes, this theorem does say negative 4 is going to be a lower bound of all of my real zeros. So if you were asked to find all the real zeros for this particular polynomial, you know you don't need to check any numbers, any real numbers that are smaller than -4. They're all going to be bigger than -4. And that's all I have for you today. I know this was a video with a lot of information. So if you have any questions, please feel free to drop them below. If you're a current student of mine, you can also email or come to office hours, and I'd be happy to help you. There's an awful lot of information. It was pretty dense. Hope you enjoyed it anyway, and I hope you get a lot of practice in on finding all of your zeros of polynomials. I'll see you next time.